Hi, my name is Anthony and I'm a practicing data scientist. Today I'm going to be talking about knowledge distillation and I'm going to be applying it to the field of computer vision. As part of my contribution for the Hugging Face community-led sprint on the computer vision course, I put together a notebook that will talk about the fundamentals about knowledge distillation and then some code to give you an example, to walk you through an example of an image classification task, starting with a larger fine-tuned model and distilling its knowledge into a student model that will be a lot smaller. Let's jump into it. So we're going to start by talking about knowledge distillation as a concept. It was first proposed in 2015 by researchers Hinton et al. Those of you who are familiar with Hinton know that he's a legend, and this is one of his biggest contributions. What it is it's a method to take a larger fine-tuned model and transfer its knowledge into a smaller model. Transfer its knowledge might be a bit of a loose terming, but essentially that's what it is. And what we ended up getting, and what we've seen over the last few years since it's come out, is it's led to two of the most downloaded models on Hugging Face's hub. So there, if we sort by most downloads, you can see that we have Distilbert, which is a very, very good model for many NLP tasks. In fact, is sometimes my baseline whenever I'm doing a Kaggle competition. That's the first thing I throw at it to try handling text data if there's some way to fit a text classification problem in there. Then there's also the Distill GPT-2, which is based on GPT-2 back when OpenAI released that and they were actually OpenAI. But yeah, so two out of the top 6 models that are most downloaded were trained by this knowledge distillation technique. So for some intuition and some background, imagine I gave you this trivia question: which of these characters is not friends with Harry Potter? Ron Weasley, Neville Longbottom, or Draco Malfoy? If I just tell you the answer is Draco Malfoy, that doesn't actually teach you a whole lot. You're just kind of learning that Draco and Harry not friends. But if I gave you that I'm pretty sure Ron Weasley isn't the right answer, I'm kind of sure Neville Longbottom isn't the answer, and I'm quite sure Draco is the answer. That gives you a lot more information about the Harry Potter universe. It tells you Ron Weasley is probably more like Harry Potter's friend. Neville Longbottom, he was kind of on the fringe, right? But he probably wasn't not friends with him. And then there's Draco Malfoy. So you get a lot more information when I tell you my thoughts about each of the answers and kind of give you my distribution over these possible answers. So that's kind of some of the intuition here. So we'll start by importing our libraries, and we're going to be distilling the knowledge from my fine-tuned model that is based on VIT base. So it's a vision transformer trained by Google and freely available on Hugging Face's hub. And what we're going to do is we're going to distill this knowledge from this model into this tiny VIT, which is just a lot less parameters, but it's the same structure. It's still a vision transformer with patches of 16 by 16. We're not going to dive into what vision transformers are. That's for another day, but we'll continue. So what we're going to do is we're going to start with the Oxford Pets dataset. It's a dataset of 37 classes and dogs. And the fine-tuned version of my VIT here had about 93% accuracy on it. These models will nowhere reach these heights of 93 accuracy, just to let you know, because these models are being trained from scratch. Their weights are all completely random, so they don't have any prior information. When I fine-tuned it, this had been already trained on a large corpus of data. But anyways, so let's take a look at the data set. And we're going to make these mappings from ID to label. So meaning if there's like 37 labels, some of them are dogs, some of them are cats in this data set, we're going to assign some of the dog types to be 0, 1, 2, some of the cats 3, 4, 5, etc. So we can actually take a look at that, just so you know. This is only important for initializing models because it'll give them some information about what it's predicting actually is in English, so it makes it easier to print out what they're predicting and things like that. So these are the 37 classes. It goes from Abyssinian to Yorkie. I actually have a Yorkie. Shout out to Bella. Let's take a look at the teacher model in action. So we're going to load from my Hugging Face repo my VIT that's fine-tuned on this Oxford dataset. And we're going to put it in eval mode because we're not actually training it. I'm going to skip over a lot of the PyTorch details in this video. So we have the auto image processor for VIT that we're going to be using throughout this video, all it does is kind of crop it down to 224 by 224, and it normalizes the pixel values, etc. And here we're going to start with the very first image in the training data set. So we have a Siamese cat. It's very pretty. So if we pass the inputs of this Siamese cat as a tensor into the processor, and we get the inputs here, we can make a prediction. And by the way, it actually isn't getting passed into as a tensor. This is getting passed as a pillow image. Sorry, I misspoke there. But yeah, it returns a tensor from the processor, and we print it, and it did in fact predict Siamese cat. So that's great. It's working as advertised. So now we're going to use this as an opportunity to talk about knowledge distillation as a concept. So what the key terms are there's temperature, KL divergence, which is the main score that we're looking at when we're trying to turn our student model into to teach it the things that the teacher model knows. Then lastly, there's a lambda parameter. So we'll start with temperature. Temperature is a hyperparameter that kind of controls the importance of what's called a soft target. And a soft target means it's not giving you a direct answer as to what the right answer is. Like the target is not like in the previous example, the target is not Draco Malfoy. The target is actually a distribution, and we actually toy with that distribution to show off the differences between the predicted probabilities. I'll show you what I mean. So if we have a temperature of 1, that means that we're not actually changing these predicted probabilities. But if we have a low temperature of 2 and a high temperature of 8, we'll see how those distributions look. So it was already ran, but so this is the initial probability. Because this model has been fine-tuned already on this data set, it was very confident that the answer was 10, which is a Siamese cat. Now, if you apply this temperature, and what we're doing there is we're actually dividing the probabilities that the model outputs by this temperature. And if we do that onto all the probabilities, we'll see that the distributions are actually a lot more, you can see, like, spread out. So even the blue ones are a little bit hard to see, but you can tell the orange one is actually, it's even wrong. So you don't necessarily want a high temperature all the time. It really depends on the size of the data set, the number of classes, things like that. But yeah, so we apply this temperature to kind of smooth out the distribution. So the blue one, you can see, is much higher than it was in the initial one before we applied any transformation. Now, the second thing we need to know is KL divergence, which is a measure of similarity between two distributions. So that's how we're going to turn the student model's outputs into the same distribution as the teacher models. And then lastly, the lambda parameter. Lambda parameter is just a weight that is applied. So we actually, in fact, take into account, I'll jump ahead to where we're talking about this math because it'll make more sense if I'm actually looking at it. When we do knowledge distillation, there's actually 2 losses we take into account, and we take a weighted average of these 2. So the first one is the standard loss that is based on the student's outputs. So that would be the normal cross-entropy loss that we normally associate with machine learning. And we multiply that by some factor related to lambda. And then over here, we have the distillation loss, and that's based on the KL divergence that I was just talking about. So that is calculated over here. We apply the loss function to these distributions, and then we apply a temperature. We multiply by the temperature squared because we had, in fact, divided by the temperature previously when we were looking at just the logits over there. So we multiply by the temperature squared to kind of balance that out. And then we take a weighted average of this loss and the standard cross-entropy loss. And that will be our final loss. So let's go back up. So here's where we were. So now we've explained the 3 main things, and that's really what knowledge distillation is. It comes down to computing a different loss function, a different objective for a model, rather than just the standard cross-entropy loss that you might see in a normal machine learning problem. We are actually computing a loss based on a teacher model's outputs. So these are some code level details that I'll kind of skip over, but this is just transforming the data with the processor that we downloaded for VITs, and then we're applying it to the data set. With transform is different because we're actually there's one code level detail that I'll mention. Normally, you might see that we would do dataset.map to apply these transforms to each example. But if you do with transform, it doesn't apply everything all at once. It applies it only when one example is called. One example is sampled from the dataset. So that is a little bit nicer on time. You don't have to sit around waiting for it to map, which is nice. And then lastly, a collate function, which is just returning the specifics of what we want. So we want the pixel values and we want the labels, and it's stacking them up in a batch for us. That's all it's really doing. It's just kind of coalescing the data into a nice format for the model. So lastly, we'll split the model into train, test, and validation sets. And then we're going to initialize a random VIT. The way we do that is we'll get the config from the already initialized VIT on the Hugging Face hub. So we just get .config. And then we configure it to our use case. So this is where those dictionaries that I was talking about come up from earlier. So if you remember, that's what they look like. And we tell it the number of labels. The reason we initialize it with a specific number of labels is because we want the classifier head at the end to know exactly how many outputs it should be configured with. Now, lastly, we can log into the Hugging Face hub to push our models into the hub, which I strongly recommend everyone do. I've already done so I'm not going to do it right now. But yeah, and then there's only a few things that you really need when you're working with Hugging Face Trainer, which is how we're going to be training the models. We just need training arguments, and we need, well, our model. We need our training arguments. We need compute metrics. So this is going to return a dictionary based on what metrics you want to see. So for now, for us, we're just going to do accuracy, but you can include F1 score in here, etc. So you can provide it specific compute metrics function. And then lastly, our trainer object. So what we're doing here is we're actually going to look at the tiny model just training normally. So there's no knowledge distillation happening here. We're just using cross entropy loss to train it based on the data set. Now, again, I just want to emphasize that these models are completely randomly initialized, and there's only 7,000 or so examples in this data set, and there's 37 classes. So it's actually a pretty tough data set to train something from scratch, and you'll see that the outputs are not very strong, but I will take a look briefly. So this was after I had done 5 epochs of training. The accuracy was around 7.7%, and then on the test set, it was around similarly 7.7%. Now, the thing that I want to highlight here is that it's still well above what a random classifier would be doing. If you just picked a random class, you would have a 1 in 37 chance of getting it right. So your expected accuracy would be around 2.7%. So it is beating random, which is, if your model's not being random, I don't know what to tell you. But yeah, so that's just training with regular. Now, we're going to do it with knowledge distillation now. So we're going to train our student model based on the outputs of a teacher model that we have been talking about for like 10 minutes. Again, the only thing that changes here for Hugging Face Trainer is that we're going to have our own custom trainer inherit from the parent class trainer, and we're going to override what the compute loss function is. Because again, we're computing our loss based on the teacher's outputs and this KL divergence with these hyperparameters, temperature and lambda, right? So we want to actually specifically calculate that loss ourselves, because unfortunately it's not like implemented for you just out of the box. You have to, this is the machine learning part of machine learning. So once we have the loss function, which this has already been implemented, the rest is the same. It's just we pass training arguments where we say like, I guess I should talk a little bit about this. This just means like how many, what's your batch size? What's your batch size for training? What's your batch size for evaluation? How often you should save your model? All of these things are captured in the training arguments. And then we initialize a trainer object with these training arguments. We pass that along here. We pass it along our collate function, our compute metrics that we talked about, training, eval set, our image processor. These are the new things. We pass it along these hyperparameters. And by the way, if we play with these hyperparameters, we would get a lot better results even. In my experiments, the accuracy went up to like 30% in some cases. So you can get a lot better than what we're doing here, but this was just for expediency. So we also pass along our student model and our teacher model. That's something else that we implemented ourselves. So these 4 things we're passing along ourselves. We specifically requested that they be part of the initialization process of this new subclass. So Once we train, we end up with about 9%. And on the test set, we have, again, about 9.06%. So after training for the exact amount of epochs, the same number of epochs, which was 5, our model was performing much better. Maybe not much better, but again, if you trained it for 30 epochs, I think you would see the difference. The test accuracy, when we just did the normal cross-entropy loss, the typical machine learning approach, it was around 7.7%. Meanwhile, when we do it with knowledge distillation, on the test set, we got about 9.06%, about 9.1%. So our student model has learned a lot in such a short time. We're very proud of it. It's worked very hard. And yeah, that's going to do it for this video. Thank you so much for watching, and I will see you for the next one.